Welcome to the training module on anticipating severe weather within summertime convection. I am Kevin Laws, a meteorologist here at the National Weather Service in Birmingham. And I'd like to acknowledge my co-conspirators Tara Golden and Leah Daly, who helped me out gathering some data and with some of the aspects of this project. Beginning with the outline, we're going to review what most of you probably already have a pretty good understanding of: pulse thunderstorms and their environment during the summer. We'll also go over the microburst. Some of you may be familiar or pretty familiar with this, and others may not. Finally, I'm going to introduce the hybrid pulse storm. This is something new that I've been working on over the past summer, and I'll show you a case study from the 11th of June 2008. And finally, I'll give you some recommendations that I learned from this past summer, and especially dealing with storms like on June 11th. First of all, most of you are very familiar with the pulse thunderstorms that pop up during the summer. A lot of folks call them popcorn thunderstorms. They seem to have a random notion to them, even though some of that myth is being dispelled. They're characterized by a moist sounding profile, in some cases deep layer moisture. Really unstable, especially due to surface heating. Although aloft they may not be quite as unstable, it may be more moist adiabatic once you get to the upper levels of the storm. Typically no organized shear, so there's not going to be a lot of storm motion, and high precipitable water values, usually greater than 1 3/4 inches. Here's a typical sounding from July of last year. As you can see, the PW values are extremely high, over 2 in this case. Cape values are pretty modest in this particular example. I think we've had some a little bit of rain here at the surface that's kind of got us a little bit stable, but for the most part Cape values will be in excess of 1,500, maybe even near 3,000 joules per kilogram on any particular summer afternoon. One big thing about the summertime characteristics of the sounding is, even though you see a little dry air here at 300 millibars, typically it'll be pretty moist from top to bottom. When you think of pulse thunderstorm and especially the characteristics of the environment of the summer, the freezing level is typically pretty high. In general, it can be above 14,000 feet, maybe even as high as 16,000 feet, or even more in some cases. How do they really form? Well, with a boundary in place or some kind of triggering mechanism to lift parcels up to the level of free convection, you usually have a pretty intense updraft, and that forces the supercooled water droplets or ice particles above the freezing level to start coalescing together. They usually stay up above the freezing level until a terminal velocity threshold is realized, or the hail, ice, and or droplets get large enough and heavy enough to fall through the updraft. There's typically limited dry air on the outside, considering the sounding profiles. They're so moist that you usually don't have a lot of dry air on the outsides of the storm to work with. What little bit there is could be entrained into the storm, and it could end up causing a cold pool at the surface. Typically you see this as an outflow boundary, obviously seen on radar, and as it crosses the surface station, cooler, moist air moves through. Wind speeds could obviously be 20, 30, perhaps even 40 miles per hour with some of the stronger storms. One thing about the pulse thunderstorm and a big time characteristic of it is that, and I think people get this generally confused, the biggest reason I think, and others may disagree, but I'm really starting to hinge on the fact that the reason you don't get a lot of hail, especially large hail, severe hail with summer pulse storms, is because as the ice falls through the updraft, it actually destroys the updraft. That's why it's considered to be a pulse storm. But also the water coating and the water loading in the updraft actually melts the hail even faster than, say, a freezing level up to 15 or 16,000 feet. So a lot of times you hear people talk about, well, the freezing level is so high, the wet bulb zero is so high, there's no way we're going to get hail at the surface. Well, that's not exactly true. I really think that it's the water-loaded updraft that actually melts the hail faster than the freezing level being several thousand feet higher than they are, say, typically in the spring or fall. So I'll say here, ice and hail does not typically reach the surface, not due to the freezing level heights, but because of the increased moisture within the downdraft. if you'd like some more explanation on this, Peter Wolf at Jacksonville did a pretty good seminar on home experiments he tried with water-coated ice and how quickly it melts in a wet environment versus a drier, say, environment. Moving on to the pulse microburst storms. Typically they're few and far between in the southeast, but definitely you can have days in the summer, usually between around June 1st to the end of August, where you can get certain environmental characteristics that shape up to form these microburst type storm. They're characterized by moist low levels, but extremely dry air aloft. That's in contrast to the typical pulse environment where the sounding is a lot more moist from top to bottom. It's usually highly unstable, and the taller, skinnier cape profiles actually become tall and fat as the upper levels moistens. I'll show you an example of that. Again, no organized shear disk as you expect in the summer, and high precipitable water values. So they're very typically the same as pulse environment, but the extremely dry air aloft really makes a big difference. Here's a sounding taken from July 21st of last year, and look at the really dry air above 600 millibars. So that should immediately jump out to you in the morning if you're looking at morning soundings. If you modify them for the afternoon heating of the day, you should immediately see this drier air aloft, extreme dry air aloft. In some cases, this obviously not only do you have a lot of cape, but you also have a lot of downdraft cape as well. Now, as I said, as a storm develops in this type of environment, what will typically happen as the upper levels start to wet bulb, the dew point will move to the right, the temperature line will move to the left. The dew point obviously moves a little bit further right than the temperature does left, but you'll actually increase the cape aloft as shown here in the example. So as the temperature profile cools and moistens with time aloft in this thunderstorm environment, you'll actually generate extreme amounts of cape in the upper levels. So how does the microburst storm form? Typically the freezing level heights are nearly the same, so surface heating allows the updraft to grow, and you have supercooled drop and ice forms above the freezing level. Ice is again suspended above, but the difference again this time is the dry stable air on the outside of the thunderstorm will get entrained into the downdraft. It will quickly destroy the updraft due to the extreme water loading, and as this dry stable air and it actually evaporates the water droplets and the hail that's in the upper reaches of the storm, and it actually forms a cold pool aloft. And as you all know, cold air is a lot more dense than, say, warm air, so the cold, dry, stable air forms the damaging cold pool that gets pushed down by the downdraft. Ice and hail usually does not reach the surface in this case, but it can, and it has been reported with some microburst cases. And I think this is due to the fact, again, you do have the water-loaded updraft just like you do with the pulse storms, but the rapid destruction of the updraft, of the water-loaded updraft, I think can cause some hail to actually reach the surface in this case. But again, it shouldn't be very large, or wouldn't be in most cases. Here's an example of one that we had on that day from the sounding, July 21st, 2008. And obviously the big characteristic that everybody looks for from, say, 12,000 feet to around 20,000 feet is this mark signature, and that is this mid-altitude radial convergence. So you can see the inbound velocities here in the middle of the storm, again from about 12 to 20,000 feet. And typically they'll all be inbounds because you only see the radial convergence. So remember, the radar only sees inbound and outbound velocities. So typically you'll see all inbounds, but you'll have an area where you'll have an area here where the winds inbound are very strong and they go to more weaker inbounds. So that's the convergence signature that you look for. Once in a while you'll get one that's strong enough to actually have some outbounds on the radial convergence too. Then you better really watch out, because your winds will be really destructive at the surface if you can get that kind of convergence. We saw that with the Montgomery storm back in May of last year, where it had 98 knots of convergence. So a few minutes later, after you see this mark signature, this is what you'll see if you have a pretty good look at it. At the lowest level, this is the 0.5 tilt, and you can see here massive divergence at the surface where this microburst hit around the Hoover area. And it's typically not good to have a storm like this right over an area, say at 6 o'clock in the evening on a weeknight, just south of Birmingham. Here we had windows broken out of the Galleria Mall, and several other incidents reported with this. I think power was out for several hours. So this is obviously an extreme case, but a pretty good look at it since it's so close to the radar. One thing I quickly want to point out too is that with all microburst storms, you're typically going to see hail, and it could be lots of small hail or some larger stones, but you're going to get the three-body scatter spike. And here you can obviously see it sticking out of the back of the storm, and this is at the elevation of 10 degrees, and just before, or here you can also see the mark signature as well. So the mark signature is here in the middle of the storm. The three-body scatter spike will also have inbound velocities, but that's not the mark signature. I see a lot of people kind of confuse that with the mark signature, but you need to look for these. Again, you need to look for the inbounds within the storm core itself and not within the three-body scatter spikes. What you're probably seeing with the three-body scatter spike is actually the updraft, because remember the beam is directed down toward the ground. So you're actually seeing the inbounds, which would actually be an updraft below the core of the storm. Okay, finally, let's take a look at some hybrid pulse thunderstorms. Now, I know this is not really a great name for it, just kind of something I threw together at the last minute, but they're characterized by moist low levels and maybe some dry air aloft, as you would see in the microburst cases, highly unstable, taller, fatter cape profiles, no organized sheerness as you would expect in the summer. One thing I've noticed with a lot of soundings and looking at these storms is there are typically lower precipitable water values, maybe even below 1.5 inches. The storms I've seen have also formed on older cold pool boundaries. So any kind of boundary that's in place that has some kind of horizontal vorticity could be a key element in the formation of the hybrid pulse thunderstorms. Here's an example from June 11th of last year. And you can see here high cape profiles. There is some drier air aloft. It's not extremely dry like you'd see in the microburst case, but it's not extremely moist either, so it's somewhere in the middle. Cape values, when modified for the day, are going to be well over 2,000 as you would expect in the summer. And again, look at the precipitable water value. This is in millimeters, 37.3. So again, it's almost like 1.5 inches here versus what you would see in a typical summer environment where the PW values are up near 2 inches. Now, what is the difference between the hybrid pulse thunderstorm and, say, the microburst or normal pulse storm that you'd have in the summer? Well, it's the presence of this mid-level rotation in the updraft. Without going into the vorticity equation, this is an old famous flash image here from the Warning Decision Training Branch. And basically what element of the vorticity equation that would be applicable here is the stretching term. Typically, the updrafts are a lot stronger than, say, in a typical pulse storm, and it creates the updraft to be stretched in the vertical. Now, as you do that, you'll have mid-level rotation to start to develop, just based on the equation itself. You can actually see it on radar, and I'll show you in a few minutes. There could be a little bit of the tilting term as well mixed in, again, if you have horizontal vorticity, say from an older outflow boundary from previous storms or storms that were nearby. Okay, so taking a look at the hybrid pulse thunderstorm characteristics, first of all, you'll have a typical summer updraft. The updraft can be intensified by some mid-level instability. So something causes the updrafts to be much stronger than, say, in a regular pulse thunderstorm. This can suspend the supercooled droplets and hailstones well above the freezing level. And again, as this updraft is stretched, you'll actually create a mid-level rotation. It's very weak, but you can definitely see it on radar if you know what you're looking for. As this mid-level rotation begins to develop, you'll also develop a counter rotation that will serve to enhance the downdraft. So it's really a synergy effect. Since the updraft is much stronger, the particles can be suspended above the freezing level for longer periods of time, the hail can grow larger, and since the updraft and downdraft have now been separated, okay, the updraft is allowed to continue. So what do you have? You have longer-lived storms, you have higher storms, and now since you have hail and supercooled water above the freezing level that's being pulled in by the downdraft. Also, perhaps some dry, stable air on the outside that can be pulled in the downdraft. As hail moves over into the downdraft side of the storm, hail is much heavier than regular raindrops, so you can actually get this separation between the actual hailstones and the water droplets. So you actually get a hail shaft developed in a pulse thunderstorm. Again, the storms don't necessarily have to be moving, but they don't have any shear to separate the downdraft. So in other words, the actual synergy effect from the strong updraft is actually creating a sheared type environment within the storm that allows the hail and rain shafts to be separated from the updraft. So this is why you can get much larger hail now at the surface, even when the freezing level is typically high, as you would expect in the summer. Hail will begin to fall through this downdraft, and since it's separated from the updraft, from the water-loaded updraft, severe hail is actually allowed to make it to the surface. Okay, so taking a look at some of the storms from June 11th, not all storms on this day were of the hybrid pulse variety. A lot of the storms were typically pulse, but you can see a lot of outflow boundaries roaming around in central Alabama, some approaching the radar site there in Shelby County and up toward Jefferson County. We're going to focus on two of these storms, one of them in northern Jefferson County north of the city of Birmingham, and the other over in Tuscaloosa County. The one in the west is in Tuscaloosa County near the Jefferson County line. Okay, focusing first on the Jefferson County storm. This storm forms near Center Point and moves south and west toward the city of Birmingham, right over the Birmingham airport. Now, typically, these storms don't have to be moving, and that's not a key characteristic at all, but it just happens to move along this outflow boundary on this particular day. Taking a look at some of the scans from the velocity, and these scans actually start in the upper left-hand corner at 1.5, so you're actually looking up into the storm. Usually, typically, at the lowest elevation scans, you won't see this rotative couplet, but you can definitely see here, north of Birmingham, the storm at several levels now, from 1.5, 2.4, 3.4, and 4.5, you can see rotation at all these levels. That is the actual updraft rotating. Here's another look just a few minutes later as the storm moves further toward the I-65 corridor and closer to the Birmingham airport. And again, very distinguishable characteristic here of this updraft that's rotating. So taking a look at it scan by scan, this is the length of the storm. Now, first of all, look at how long the storm persists, from 21:53 to 23:22 or so. So nearly an hour and a half on this storm, and typically pulse storms are about 30 to 45 minutes. The red here is greater than 60 dBz, so I want to show you how the core in the storm actually goes up and down. And take a look here. This storm actually has several pulses where the updraft gets re-energized and more ice and hail is able to be formed twice within the storm. We actually got 2 damage reports. Now, taking a look at the rotational velocities, I've taken several elevation scans, averaged out the rotational velocity, and showed you what the actual physical number here is above each scan. First of all, the storm pulses up at about 22:27, and you can see here how the rotational velocity is increasing or decreasing with time. So we go up to 22:40 or so, and we see 12.2. Again, it's not very strong rotation like you would expect with a mesocyclone, but definitely an indication here of rotational velocities increasing within the mid-levels. At 22:44, the storm has reached its first peak, and you can see here it's beginning to crash. It crashes down back to 10.7, and then take a look at 22:53. As you're getting damage at the surface, the rotational couplet is actually increasing once again, and you can see the storm is going through its second life cycle. Then the second collapse happens around at 23:09, and that's where we get our second report of severe hail. Again, in both cases, the reports were received right where the red oval is indicated, and both reports were well over an inch of hail. And again, it's June 11th, and you saw the sounding. no shear to be had. The freezing level is particularly high on this day, around 15,000 feet. The hybrid storm is notorious for creating severe hail reports at the surface. The second case is I won't get quite as involved, but you can see here it forms just in between the Brookwood and North Johns area in central Alabama. This again is the Tuscaloosa-Jefferson County line. And quickly running through some of the updraft characteristics, you can see here 1.3 up to 4.3 on the 4-panel scan. Definite indication of rotation at the mid-levels on all 4 scans here. Okay, so let me try to give you some tips on anticipating severe weather, especially with the hybrid storms. You'll need to watch for rotational couplets at mid-levels, between 12 and 20,000 feet. And you'll obviously have to do that with the velocity base data or SRM product would be fine. As these updrafts are gaining strength, it's almost like a synergy effect. So as these updrafts are being stretched, you'll start to see vorticity at the mid levels, and then you'll see this is really your first indication that you will have a potential for damaging winds and hail at the surface because you're getting that updraft downdraft separation starting. The second indication will be the leveling off of the rotational velocity, and that's about when the updraft reaches its maximum potential. Storm top heights will be a lot higher than probably the adjacent storm that exhibited no mid-level rotation, so watch your storm top heights as well. And then finally, as the storms begin to decrease, as that rotational velocity begins to decrease, the cores will be collapsing. By this point, it's almost too late to issue a warning with any appreciable lead time. So, and you also need to watch for rotation to increase again at mid-levels, so that may mean a second updraft cycle is forming. The bottom line is this, though. The storms that exhibit mid-level rotation are more likely to produce severe weather than, say, ordinary summertime pulse convection. Okay, so what are some recommendations for identifying the environment of the hybrid pulse storm? First of all, know your environment. Here at the National Weather Service office in Birmingham, we have set up typically a spreadsheet that can be used any time of the year. But what does the spreadsheet really do? Not only are you entering the numbers, you're not blindly doing so. You're actually investigating the sounding. You're modifying the sounding, how it's going to look later that day. So knowing your environment, knowing if dry air exists aloft, knowing what kind of cape profiles exist, and knowing the shear characteristics of your environment for that afternoon are really key to understanding everything about convection. Another recommendation, watch out for the mesoscale boundaries. They're obviously seen at the 0.5 elevation scan through Rayleigh and Bragg scatter, so you can definitely see where new convection is going to develop, and possibly the hybrid storm developing on some of these outflow boundaries where you have horizontal vorticity. Finally, something very simple that people don't usually think about is changing your color scale. Here we've gone to 8-bit for several years now, and a lot of people still try to apply the old 4-bit schemes to their 8-bit data. Change your red and greens if you need to accommodate the summer. I've introduced a new color scale here for summer velocity readings, and you can see how indeed you can pick out some of the mid-level rotative couplets. Look how much easier it is to see now that I've just made some simple modifications to the lower level velocities, say from the bottom right that you would typically use, say, more in the spring or fall. But this is the case for any time of the season that you may want to change the way you traditionally have viewed radar data. Something very simple, a lot of people don't think about it. Okay, that's it for this local training module. Hope you enjoyed it. Thanks again for viewing.